So I wanted to do a brief video to show you how to set up the method of truss problems within the final homework that you'll have in the course. So here we have a truss. It's subjected to 3 external vertical loads, P1, P2, and P3. So it looks like the loading associated with a bridge truss, as we talked about earlier within the Chapter 6 lectures. We have a pin reaction at A and a roller reaction at G. So this would have 2 unknown reaction forces associated with it, and this would only have 1 since the roller can't oppose translational motion. So we're interested in solving for the forces developed in members LK, KC, and CD. So LK, KC, and CD. And whenever you're debating whether or not to approach a problem through method of sections, you ask yourself, well, am I interested in the forces developed in a small enough number of sections such that if I were to partition the entire truss into 2, I can draw an internal line that divides each of the sections of interest. So if you notice, if I draw a line like I've shown here, that would have the capability to partition the truss into a left section and the right section, and it would partition the members LK, KC, and CD. And if you remember back to the prior learning module, when you actually draw the 2 separate free body diagrams, you would replace at the point of partition at the point of partition, you would draw in the internal tensile force that we're assuming exists in each of these members. So if I were to break this into a left part and a right part, hopefully the first thing you notice is the left part of this free body diagram, it will have 3 unknown forces associated with the 3 members that we partitioned. But in addition, it's going to have this unknown reaction force at A. So before we begin, what we actually would need to do is to determine the reactions of that. And I'm saying reactions, but of course, that consists of 2 parts. And since this is just meant to be a quick video to get you set up, I'm not actually going to draw a free body diagram. I'm just kind of going to trace around what you need to do. Actually, I lied. I'll draw a little one just to get the key point. Because the key point here is oftentimes in your free body diagram, you only need to show the various forces of interest to you. So I have the reaction here at G. I have the vertical reaction to that, along with the horizontal reaction. So this is RAY, RAX. And in addition, I have these 3 loads, P1, P2, and P3. And these are applied at 2-meter increments from point A. And it's also going to be important to note that the distance from point P3 to G in the horizontal direction is 6 meters. And we can add up and determine what the, from this dimension, we can determine the perpendicular distance of each of these vertical forces from point G. Because you can guess, the first thing that I'm going to do is enforce rotational equilibrium about point G. And what that's going to allow me to do is isolate RAY. And we'll talk about, obviously, hopefully you see RAX is 0 just by inspection, but we'll show why that is in a minute. So if you sum all the forces, sum all the moments rather, about point G, what you'll find is that pinning it here, you'll notice that RAY is going to introduce a clockwise rotation. So that's going to be minus RAY times that perpendicular distance separating the vertical line of action of RAY and RG is 6 plus 2 plus 2 plus 2, or 12 meters. And that reaction at A, the vertical reaction, which is rotating in the clockwise direction, is serving to counterbalance the clockwise rotations associated with P1, P2, and P3. So those are all going to be positive. P1, if you notice, is going to be 2 meters closer than RAY was, so there'll be 10, plus P2 is going to be 8 meters away in terms of the perpendicular distance, and P3 is only 6 meters away. So I went through that a little bit quick because hopefully everyone is pretty familiar with doing this now. So you know these values, which means you can solve for RAY. And I'll let you do that since that is a homework problem. But the ideal is that once you've determined RAY, and so this is kind of like the first equation of equilibrium that you need to enforce. The second is we know that if this entire body is in equilibrium, And under the particular loading conditions that are shown, there's no horizontal forces. What that means is that RAX is 0. And you might ask, well, why would they have a support in there that has the capability to oppose horizontal translation? Well, this is just one loading condition that this truss would be subjected to. If there were a loading condition that induced translational motion in the horizontal direction, you would need this, and that would change. So this is kind of like your external analysis that you often do first in a method of sections type problem. Step 2, you want to partition the truss across the members of interest and basically redraw a free body diagram. And what we should find now is that that free body diagram is statically determinate, meaning that we have the ability to enforce 3 equilibrium conditions. And that's good because we only have 3 unknowns. So here is point A, and I will know RAY from that external analysis that I did. So I'll say that that is known. Here at B, I'm going to have P1 in the downward direction. And I know this is 2 meters separated. And then in addition, over here to point C, I'm going to have P2. And again, this is 2 meters separated. And in your free body diagram, you can mark in, okay, this is A, this is C, this is B, particularly when you have a simple truss that is very periodic, meaning that a lot of sections are just replicates of other sections. It's useful just to, when you look up, you make sure that you didn't leave off any of your truss. So notice that once I go from, draw the line segment from L to K for that member, that's one of the members in the original truss that we need to segment in order to solve for that internal force. So recall that when we segment a member in the method of sections, we'll replace, at the point of partition, we'll add in the tensile forces. We'll call that FLK. That is good. And in the other member that we segmented here at point C, so this is C. If you notice, I should have not drawn that in there directly where I did, so I'll mark it back down here. What I'm drawing here is the tensile force that's developed in member CK upon segmentation, so that's FCK. And then I've segmented also off of section C, member CD, so I'll draw in. You knew wherever I drew the C, I was going to, this is what I get for not thinking in advance about the diagram that I need to draw. So there's C, this is point B, this is point A. So this, from here, we can enforce equilibrium, and that is going to be statically determinate because there are only 3 unknowns. And kind of following that concept which we spoke of in the last learning module from the text, the easiest way to go about solving these is to, are we good? Yep, sorry, I was just looking over it one more time to make sure. And it's always a good habit. Just, you can probably see on my .chem, make sure that you have the original portion of your truss with all the members that weren't segmented left intact, and make sure that every member you segmented, LK, KC, and CD, you've replaced with a tensile force along the line of action of the member. And you could draw the kind of mirrored free body diagram if you want, but we know that this is the one we'll be interested in, because if we were to solve the one on the right, we don't even have the angular information here in order that we may need. In addition, it's just easier to work with the portion of the truss on the left. So the easiest way in terms of solving for the forces of interest, the first thing you want to do is step 1, enforce rotational equilibrium about point C. And the reason you want to enforce rotational equilibrium about point C is this will allow you to solve for FLK. And in order to solve for FLK, when you think about the things that you're going to need the vertical displacement from point C to the line of action of LK. That's your perpendicular distance. And we know that that's 3 meters. And notice if you pin at C and rotate about LK, that will be a clockwise rotation. So that will be negative. So that's going to be minus FLK times 3. So you got that force taken care of. We don't need to consider the moment about point C of any of these three forces because they all pass directly. They have lines of actions that pass through point C. We do need to consider the rotation of P1 about point C. And if you notice, that will be a counterclockwise, so it's going to be positive. So I'll say P1 times 2. Again, since it's a purely vertical force, the perpendicular distance that we need is just this horizontal distance of this member, which is 2 meters. And in a similar fashion, we're going to have a clockwise rotation that's going to be minus. And it's going to be associated with that reaction, the vertical component of the reaction today that we solved for beforehand. And it, since it has a vertical line of action, its perpendicular distance will just be the distance from here to here, which is 2 plus 2, or just 4. And we know that is equal to 0. So you will know this from your external analysis. We're given this to be 21 kilonewtons. So you're going to be able to solve for FLK. And then once you've solved for FLK, from that, what you want to do is sum all forces in the x direction and set those equal to 0 using a positive sign convention. You could use negative, but that's the way we usually do it. And what this is basically going to show you, if you notice, is that FLK, is equal to minus FCD. So these are going to have equal magnitude, but opposite direction. So if you think about it from a sign point of view, if in solving this, FLK turns out to be positive, which it's hard to say without having these numbers whether or not it will, that would mean that FLK is in tension, which means that FCD, it has the same internal force in it, but it is in compression instead. And then once you have that, or these orders can really be switched, you'll want to enforce translational equilibrium in the vertical direction. And what you will find here is that FCK equals, FCK, I'll write it this way just to make it clear, equals P1 plus P2 minus RAY. And that's to say the external loading that's applied to this portion of the truss, P1 and P2, FCK is responsible for offsetting whatever portion of that external loading isn't already picked up by this reaction at AY. So hopefully that makes sense. You can solve for this, you can solve for this. And I should say over here, you can solve, you already know FLK from here. So you can solve for FCD, you can solve for FCK, and you solve for FLK in the first system of equations. So you see the method of sections is not too bad. Maybe you want to be careful with the naming convention that you choose for representing those internal forces. I had to be careful as I was writing it to make sure I was very clear what those said, but that's okay. So pretty straightforward problem. Hopefully on the homework, it won't be too confusing for you. The other homework question that I'm going to give you from chapter 6 is one on disassembly of machines. So I'll do a brief lecture kind of introducing the basic concepts like I did for methods of sections. And then I'll do a video that shows you how to set up the homework problem if you'd like.